Thank you very much for having me. Thank you for inviting me. Thank you for that introduction. So this talk is called Ingredients of Intelligence, and in my research, I have two hats, one as a data scientist and one as a cognitive scientist. And today, my presentation is about building machines that learn and think like people. There have been two storylines in AI in the last few years. One is focused on the breakthroughs. We're now approaching or exceeding human-level performance on a range of difficult, interesting tasks, including object recognition, speech recognition, playing board games, playing video games. And the other storyline has been about the return of brain-inspired computation, also known as neural networks or deep learning. And these algorithms take loose inspiration from the brain in terms of their basic elements of computation and also their multi-layer architecture. Let's consider these two narratives together. If we have machines that can reach human-level performance on a range of interesting tasks, and they use brain-inspired computing principles, how close are we from building machines that learn and think like people do? Often, the media acts like we're already there. So when the DeepMind work on playing Atari came out, here are some news headlines that were talking about this exciting work. There are headlines like, "This AI learned to play Atari games like humans do, and now it beats them." Or, "Game playing software holds lessons for neuroscience." When AlphaGo came out, there were headlines like, "Scientists have made artificial intelligence strides in recent years, making computers learn and think more like people do." And in addition, how Google's AlphaGo imitates human intuition. So, do we have machines that can learn and think like people do? We should think seriously about this question. And I don't want to be a pessimist, but I do want to be realistic, and I think the answer is no. In so many ways, AI is more limited, and I think we should take insights from cognitive science and human intelligence in order to build smarter, more human-like artificial intelligence systems. So here are some examples of ways in which the state-of-the-art in AI and human intelligence are quite different. People extract more knowledge from less data compared to the best current AI systems. In addition, people build rich, flexible models of the world, while current AI is largely driven by powerful pattern recognition techniques. And third, finally, it's not a matter of just scaling up current techniques to more data and more compute, that there are key cognitive ingredients that are either missing or underutilized in current AI today. So that's what this talk is about. So how do we build machines that learn and think like people do? Here is an outline of my presentation. In part one, we're going to introduce two challenge problems for building more human-like machines, the characters challenge and also the frostbite challenge. And then in part two, we're going to review progress on these challenges and discuss the most promising directions forward for making additional progress. Much of the argument in the talk today comes from a paper I co-wrote with Tomer Ullman, Josh Tenenbaum, and Sam Gershman called Building Machines That Learn and Think Like People. And in this paper, which was published in Behavioral and Brain Sciences, we go into great detail about all the topics in this talk today and many others, and what it would truly take to build a machine that learns and thinks like people do. So if you're interested, I suggest this is a great place to start. And one of the key points that I mentioned is that people can extract more knowledge from less data compared to the state-of-the-art in AI. So let's talk about object recognition and concept learning for a moment. The state-of-the-art in object recognition works by training very large-scale deep neural networks on very large amounts of data. So to be able to recognize t-shirts or elephants at the level that you and I can, the standard dataset ImageNet has 1,200 examples of different t-shirts, and 1,200 examples of African elephants, and 1,200 daisies, and so on. But you don't need that much information in order to pick up a new concept, and neither does a child learning the words of their native language. To give you an example, when the Segway came out, you might only need to see a single image of a Segway or see one person briefly riding it for you to understand what a Segway is, for you to completely get the concept and be able to recognize other examples of a Segway that differ in their underlying features and be able to exclude all these other objects that otherwise look quite similar. So you can learn extremely quickly, much quicker than the standard techniques for training object recognition systems. And in addition, once you have the ability to recognize something, many other abilities come along for free. And you can parse a new concept into its most important parts and relations. You can generate new examples. You can sketch your own version of a Segway. You can even think up a new concept that combines aspects of other concepts that you already have. So this is what we mean by building a model rather than just doing pattern recognition, that your concept, which you picked up extremely quickly, is rich enough and flexible enough that not only can you use it for recognition, but you can use it for all these other tasks as well without having to retrain, just by simply applying this model of the concept in a new way. To get at this ability, we introduced the Characters Challenge, which is a challenge for AI to tackle more human-like learning problems. And we looked at handwritten character recognition, which is a popular AI benchmark, and actually the best computer vision algorithms today were developed specifically for this problem of recognizing handwritten digits. Yet there are key differences between your ability to learn a concept behind a handwritten character and what standard techniques in machine learning can do. And the differences are much like the Segway case. Even though these concepts are much simpler in every way, again, you can pick up a letter from a foreign alphabet that you've never seen before and be able to recognize it again in someone else's handwriting. Or you can parse, you can generate new examples, or you can think up a new letter in the style of a novel alphabet that you've never seen before. So even for this simple concept, again, you learn it extremely quickly and you learn it in a very rich way. The second challenge that we introduced in the paper is called the Frostbite Challenge. And this is based on the Atari game Frostbite, which is a popular current benchmark in machine learning. And the Frostbite Challenge is the challenge of learning to play a new video game like a person does. So in this demo, I'm going to show you a quick clip of the Frostbite Atari game. And I just want you to watch what's going on and try to think about what the goals of the game are. How would you complete a level? What's the agent trying to do? So here we go. Looks like we may have another video issue, but that's okay. Well, I'll describe it rather than watch the video play. But so imagine the agent over here is going to hop across the ice floes, and they're going to turn blue every time they're touched. And then, okay, very good. Let's see if that'll play. No luck. That's okay. So here's an illustration. So the agent starts on this terrain, this surface at the top of the screen, and then the agent hops across the ice floes and they turn blue. Now every time the agent touches a new ice floe, she gets another brick of her igloo. And you can clearly see that the agent is avoiding certain objects, like the birds, and actually trying to approach other objects, like the fish. And just from a very brief clip of this game, you can pick up all that knowledge. So your cognition is incredibly rich. And you understand the key objects, the key agents, the physics of the game, and you can think about the complex sequential plans that the agent is taking in order to achieve the goals of the game. So you may only need just a short clip of someone playing the game in order to pick it up. And as with the Characters Challenge, people can learn much more quickly than the state-of-the-art in AI can learn. And as I mentioned, Atari is a very popular benchmark that was popularized by Google DeepMind with their work on the deep Q networks, which has had a tremendous impact in the last few years. And recent versions of the DQN and its siblings have come close to reaching human-level performance on Frostbite and other interesting video games. So to show you this graph, on the y-axis, we have the Frostbite score. And the red stars are different humans playing the game, and you can see what score they get. Now, on the x-axis is, so what you can see here is that the DQNs, the AIs are getting close to human-level performance by the end of training. But it's important to look at the x-axis, which is the amount of experience required in order to learn the play. And you can see here that the point all the way on the right-hand side is 900 hours, which translates to roughly 36 days of playing nonstop Frostbite in order to get to human-level performance, where you can play for 5 minutes and get a score somewhere where the red stars are. An example of just the difference in terms of amount of experience required. And much like with the characters, people learn a much richer representation. So you are not tied to a particular objective or score function once you've learned to play the game. I can give you a new objective, and I can tell you, okay, your goal is no longer to try to get the highest score in the game, but maybe you want to get the lowest score. Or maybe you want to get a score that's close to a nice round number like 100 or 300. Or maybe you're playing against your friend who's never played before, and you want to beat your friend, but you don't want to embarrass your friend, so you just want to beat them by a little bit. Or maybe you want to collect all the fish, or you want to find all the Easter eggs, or you want to go as long as you can without dying. So I can give you all these new variants of the game, and you don't have to retrain. You can immediately reconfigure the model that you've learned for Frostbite in order to tackle any infinite number of variants for the task. And again, an example of what it means to build a world model and why it's so important and so key to human intelligence. So just to be clear, that the DQN, once trained on the version of getting a high score, can't do any of these other versions of the game without retraining. So the Frostbite challenge is about these two pieces together. Rather than just reaching human-level performance, let's try to build AI systems that can learn in minutes of experience rather than hundreds of hours, and then learn a representation as flexible as the one that you have. So I'll tell you about some of our work on tackling the characters challenge, where we develop an approach that can handle all the different tasks on the slide, and I'll tell you about it. And to develop the challenge, my collaborators and I collected the Omniglot dataset of handwritten characters, where if you're familiar with MNIST, which is a very common benchmark in machine learning, MNIST has 10 different concepts, which are the digits 0 through 9, and it has about 6,000 examples of each of those different letters. Now, Omniglot is like the transpose of MNIST, and rather than having just 10 different concepts, it has over 1,600 drawn from alphabets around the world, and it has just 20 examples, 20 different people writing each of the different characters on Mechanical Turk. So it's a much better human benchmark, because there's many concepts, just like we all have many different concepts that we've learned, and the challenge is to learn it from a small amount of data. So here's a demo that's going to help us understand how the algorithm works. So I'm going to ask for your participation here. If everyone can hold up their writing hand to about eye level. Okay, very good. So on the count of 3, we're all going to draw this letter together. Is everyone ready? 1, 2, 3. All right. Awesome. So I saw a few hundred people do roughly the same thing, and that's what everyone in the data set also did that produced these letters, where you first draw something that looks like a 3, which is represented by this red stroke here on the screen, and then draw this other stroke hanging off of the 3. Now, a 3 has 2 basic motions that are composed in order to produce the first stroke, right? There's a motion, there's a brief pause of your hand, and then another motion, and then you lift your pen and you go over and attach the second stroke to the 3. And this is what we found all across the omniglot data set. So again, the video is not going to play, but if you can pick any character in omniglot and look at 20 random people on Mechanical Turk drawing it, you'll see a tremendous amount of consistency in terms of the parts that are used, the decomposition into basic parts, and also the order and direction in which those parts are drawn. So there's commonality on people, commonality for people across all these novel letters that they've never produced before. For the characters challenge, we developed the Bayesian program learning algorithm, which was our attempt to develop a computational framework that learns more like a human does. The goal of the model is to do what you all did in that demo, is to get one image of a novel letter that it's never seen before and infer a structured program, a set of subparts, parts, and relations, a formula for producing new examples of that letter. So that's what the BPL algorithm does, which was published in 2015 in the journal Science. And it's a Bayesian program learning model. So because we're Bayesian, we have a prior distribution over programs. So programs are represented here as theta. And this is your prior expectations about the subparts and parts and relations that go into letters in general. And then there's a renderer, which is the likelihood that tells you, given the program, what does it look like when I render it as an image? And then with those two pieces, we can reason about the distribution on likely programs, theta, given the image I, with our posterior distribution. Now, there are some key ingredients for learning good programs, which come directly from this idea that people draw novel letters with a lot of consistency. And these ingredients are causality and compositional learning. So let's go into a bit more detail about these ingredients and why they may be so important in human-level intelligence. So causality is the basic idea that you can have more powerful learning by inverting the generative process. For letters, this means that you can explain a lot about visual appearance, why all these twos look rather different in pixel space, by thinking about their causal properties and thinking about the causal generative process that actually produces the images of those twos. And it's not just about letters. If you think about a tree, so of course you can train a deep neural network based purely on visual features to be able to recognize a tree and distinguish it from other types of objects. But your concept of a tree, your model of a tree is so much more than that. Because you can answer questions like, is this tree growing too close to my house? Or if I want to trim the tree, but I want to trim it in a way so that it doesn't grow too much, but I also don't want to kill it, right? There's all these judgments or reasoning you can use your concept for in order to reason about objects in the world. And causality is at the very center of those concepts. The second ingredient is about compositional learning, which is a very old idea in AI and cognitive science. It's this idea that you can build more complicated representations out of simpler parts that are recombined in new ways. And to give you an example for the segue, once you learn, by the time you learn what a segue is, you already know about all these other vehicles. So you know about bicycles, unicycles, mopeds, and so on. And you know about their parts. So you know about wheels and handlebars and posts and seats and motors. And you know about relations between the parts so that motors power the wheels and that handlebars sit on top of a post and so on. Then, armed with this compositional knowledge, once you see a segue, if you parse it in terms of that representation, those sub-concepts you already have, it provides a much better basis for generalization that could allow you to recognize new examples or generalize in very rich and powerful ways. So that's the basic idea behind compositional learning. And so given these two ingredients, we're going to do causal compositional learning of letters. And this is how the BPL algorithm works for characters. Here's a specification of the generative model. So we have a probabilistic program here, so a piece of code that we can run. And every time we run it, we sample a new type of letter. So we may sample the letter that we all drew together. We may sample an alternative one. And the process for sampling letters goes by first sampling how many parts we want, how many subparts we want for each of those parts, how the parts are connected together with relations, and all these parameters are learned from a part of the data set that I showed you, part of the omniglot data set. So general properties of the concepts in the world are used to fill in the pieces of this prior. And this program, once it runs, it returns another probabilistic program. So it returns a handle to this program called generate token, which adds motor noise, and every time you run it, it produces a different variant of the same character. So it might be the difference between how you would draw a letter A and how I would draw a letter A. So slightly different tokens of a particular character. So now we have a generative model that samples another generative model, and this is the math behind the algorithm, and we can use these two pieces to do probabilistic inference and reason about the most likely programs given any image that we have. So we evaluated the model on a range of different tasks, and it includes all the tasks that I have on this slide. So if you want to go check out the paper, if you want to know about the nitty-gritty of each of these different tasks, I'm going to highlight just one task here, which is about generating new examples. And what we did in the generating new examples task is that we picked some novel letters that were unfamiliar, and we gave 9 different people on Mechanical Turk the chance to draw a new example of that letter. So not copy it, but to produce a new example. So for instance, look at that image at the top left of the screen. 9 different people produced a new example of that letter, and we asked the BPL algorithm to do the same thing. Can you sample 9 new examples given the same image that people saw? So you can think of this as a visual Turing test. Can you tell the difference between the characters generated by the algorithm versus the ones generated by actual people? So one of these 2 grids at the top left, A or B, is the machine-generated letters. So I'm going to, again, this is an audience participation moment, so I'm going to give you a chance to make your prediction, A or B for top left. Which do you think is generated by the machine? Okay? So I'm going to ask you to raise your hand. Can you raise your hand if you think A is generated by the machine? Okay, very good. What about B? Okay, exactly 50-50. Let's try the one in the bottom right. Okay, I'll give you a second to make your predictions. Who thinks A is generated by the machine? Okay, what about B? All right, again, you have a competitive race. So I'll show you the answers here. So the red are the grids generated by the machine. It can be hard to tell. Judges were essentially at chance. And we applied the BPL algorithm to all the rest of the tasks in the characters challenge, including one-shot classification, identifying letters written by somebody else, or examples of the same letter written by somebody else. We did other versions of the visual Turing test where this time you actually get to watch a movie of the person drawing and the algorithm drawing to get more information about whether you can distinguish which is which, and we did another visual Turing test for that. We did a generating new concepts task from a novel type, so you get a novel alphabet, and ask people to invent a new letter that looks like it belongs to that alphabet, and again with a visual Turing test. And we did the same thing with generating new concepts without constraints, and across all these different tasks, either the algorithm reached human-level performance, or most judges in the visual Turing test couldn't distinguish the difference between the human behavior and the machine behavior. So in sum, BPL was the first time in machine learning or cognitive science that we have an algorithm that can learn real, rich visual concepts from raw data and produce human-like behavior across a range of different tasks. And we've since applied the approach to applications in learning other types of visual concepts, to learning simple speech concepts like picking up a new word or a new name, or even for machines to ask human-like questions, to think up new questions when they're trying to learn. So, do we have our answer? Are compositional learning and causality the missing ingredients? Armed with these 2 ingredients and human-level performance and brain-inspired computational architectures, do we have machines that learn and think like people do? No, we don't. People are much more complicated still. There are many other ingredients that are studied heavily in cognitive science that are absolutely critical to our minds and cognitive development that I think are also critical for developing machines with the same capacities that we have. These ingredients include intuitive physics and intuitive psychology and many others. And let's reflect again on the Frostbite challenge, which remains very much an open challenge in AI. When playing Frostbite, part of the reason why current algorithms take so much data is because they're spending a tremendous amount of time learning about basic objects and dynamics in the game. So they're trained from scratch, and they have to learn what are the objects, how do they evolve over time, and so on. Where we know from the work of Liz Spelke and other developmental psychologists that within the first few months of life, an infant has rich expectations and understands key principles about how the physical world works, including all the different principles that are shown on the left-hand side of this slide. So rather than learning from scratch like current AI systems, babies have these principles basically as soon as you can test in the lab. And by the time anybody learns to play a video game, whether it's a child or an adult, you would immediately parse the scene in terms of these objects and dynamics and physical principles that you already have, which saves you a tremendous amount of time learning about those properties, where current AI is spending lots and lots of data, cranking through, trying to learn everything from scratch every time. Intuitive psychology is similar. Again, infants can reason about agents, their goals, and how to efficiently achieve them from very early ages, the first few months or years of life. And again, these are very difficult concepts for machines to pick up, like what is the goal? Is this avoiding me or is this tracking me? But they're fundamental to how you understand and would learn a new game like this, and it's important that we find ways to include them in machine learning algorithms as well. For scene understanding, we also need all of these ingredients together. So here are some example scenes, and if I ask you to produce just a one-sentence summary of each of these different images, you might say, here's a person who fell off their motorcycle, or here's a plane that's about to crash, or a natural disaster by the coast, and these people are fleeing and probably very scared. But if you give these images to a state-of-the-art caption generation deep neural network, you get captions like this: a man riding a motorcycle on a beach, or an airplane is parked on the tarmac at an airport, or a group of people standing on top of a beach. So they're not wrong, right? The bottom-up features are there, and that's what current algorithms base their decisions on. But it's completely missing the wrong causal model, failures of compositional learning, failures of intuitive physics and intuitive psychology. And to get human-level scene understanding, we're going to need those ingredients as well. Is this an academic exercise, or is this approach going to impact the technology of the future? Well, I already mentioned scene understanding and why I think these ingredients are so important, but also let's consider autonomous driving. If you want to have perfect autonomous driving, it's not enough just to detect a pedestrian. That's not how we drive or we understand pedestrians. We detect their goals, what they're trying to do. Is this person paying attention? Are they looking at my car? Are they wandering across the street looking at their phone? Is it a child running into the street to try to catch a ball? So this is how we understand the actions of others, and these concepts are critical for how a machine should behave in these situations. So I think to get perfect autonomous driving, we're also going to need these ingredients. For intelligent assistance, it's not possible to pre-program or pre-train AI assistants to have all the concepts that they need in order to be truly intelligent when you get them out of the box. They have to be able to learn new concepts on the fly very quickly from few examples, just like a child does. Or also for creative design, I think these ingredients are essential. Okay, so how will building more human-like machines change society? AI is certainly making a lot of progress, and it's changing the economy in interesting ways, but there's still a huge gap between human intelligence and machine intelligence, and in my opinion, it's not going to be closed anytime soon. So when thinking about the future of work and where AI is going, I think the conversation should be about how we best should work together, building on the very different strengths that AI currently has and what people currently have. And if we want to build the next generation of algorithms, AI is going to need more ingredients from our own intelligence, and I believe that cognitive science and the study of our own mind will play a key role in developing the next generation of more powerful and more human-like AI. Thank you.
Thanks a lot, Brenden. So, rapid fire question. Let's start with Michael Marushan. Gentleman in yellow. It's yellow, right? Yeah. What's the topmost principle, mechanism missing in current AI space from psychology?
Yes, that's a great question, and so there's 5, and I covered them all briefly in this talk, but check out that Building Machines That Learn and Think Like People paper if you want to know about the nitty-gritty and the cognitive and developmental origins of all these ingredients. So intuitive physics, intuitive psychology, compositionality, learning to learn, so basing new learning on top of previous learning, and causality. So I think those are all key principles that have a long history and decades of work in cognitive science that AI is currently underutilizing or is really absent altogether in current systems.
Then Jan Shinkora, back there. How much of human knowledge is incorporated into the written character model? What would it generate just from the priors?
Yes, that's a very good question, and it's a mix of some of the knowledge is hand-engineered and then a lot of it is learned. So the basic thing that we give the model is if we tell it that letters are made up of strokes, that there are these basic parts, and we don't tell it what a stroke is, but we say that a letter is composed of these basic parts. So if you sample from a completely uninitialized model, you get just a bunch of squiggly things sort of all over the place in a disconnected way. And then after the learning, it learns that, okay, there's common strokes that repeat across many different alphabets. There are straight lines and horizontal and vertical, and there's certain types of curves, and these are the ones that tend to follow one another, and all of that is learned. And then once you do that, you can start sampling nice-looking characters. But the key thing and what gives the approach the most juice is having the right causal model. So in an abstract way, getting the strokes precisely right isn't as important as knowing where your data comes from, and that is constantly what our minds is trying to do. When we learn something new, when we're exposed to something new, we want to understand where did it come from, why is it there, what's its function. So that notion of causality was the most important thing for the algorithm, and I think is also one of the most important things for our understanding of the world.
Then experimental psych question from Lukas Linhardt. Up there. Has the letter writing consistently held even across cultures, as in letter versus character writing, LTR versus RTL writing systems?
Yes, that's a very good question, and so the data set was collected very broadly from writers all over the world with different backgrounds and experiences with different alphabets. And we've done some cursory analyses with that, but if you're interested, again, like that data is available and you should check it out if you have your own hypotheses. What we find is broad consistency. And really there's some general principles that people want to use as few parts as possible, and like straight lines and simple curves and circles seem to be universal across different backgrounds and different alphabets and different cultures. Also the direction in which strokes are drawn, almost everybody starts in the top of the letter and draw it down because it's easier in terms of motor constraints in a lot of ways. And if you're right-handed, you write left to right, and if you're left-handed, you write right to left for individual letters. But otherwise, we haven't found that many differences. Even in scripts that are written right to left, often the characters are still written left to right. So there's a lot of interesting universals, and I think that's the key point of what we found.
And then quick shout out to Martin Yasso. Did the rest of his talk answer your question about the networks versus humans? Or do you still want to add? Okay. So Martin was wondering, don't you think saying that people learn from less data is a little bit or more misleading? You are omitting the fact that people saw a million other data before seeing that one segue. They saw vehicles, wheels, handles. But for the neural network, it is the first thing it sees. Want to comment on that?
Yeah, and that's a very good point, and that's a common response we get for this line of argument. And I think it's another way of saying the same thing, that people, whenever they come to a new task, whether it's learning a new letter, learning what a segue is, learning to play a new video game, has an incredibly rich starting point. And that starting point might be learned, and might be learned through transfer learning, through a bunch of other experience in the way that you're suggesting. suggesting, certainly that plays an essential role. There may also be architectural ingredients that aren't learned that are, again, playing an important role in that richer starting point. But the key point, however you want to think about it, whatever you think that richer starting point comes from, is that it's there, that we have a tremendously strong prior whenever we're learning something new. And rather than always treating machine learning and AI problems as we have to learn from scratch, we don't want to build in anything, and we always want to tackle each problem in isolation from scratch, I think we shouldn't try to shy away from tackling problems in the same way that people do, which is with a richer starting point, with prior experience, and therefore try to learn it from less data and be able to generalize in far richer ways than what we can currently do in machine learning.
Okay, let's thank Brenden again.